Hey guys, what's up? Dr. Tickle here. I know it's been a while since we did some videos. That's because I was ill, and then I had my family around, so I couldn't really get any quieter with my parents' dog being around. I was tempted to do a video and have the dog on my lap, but I didn't think it would be very appropriate. So let's get back into this. So 102 CD, 102 CM. So now we're over halfway through the module. We finished all the DC stuff now, so we're going to get in and start looking at AC circuits and phase relationships. There's going to be a series of 4 short, probably about 30-minute or so videos, which will cover all the AC circuit theory, and then that'll give us a basis so we can go on and move on with magnetics. So let's get into this. So this comes from chapter 9 of the Hughes book. So we're going to look about AC circuit definitions, we're going to look about AC circuits, phase relationships, introduce phasor diagrams, phasor notation, and then that'll lead into the topic 10 video where we start looking at complex numbers. So again, chapter 9 of Hughes and chapter 5 of the Hamley book is some good reading to look at. So yes, so let's crack on. Okay, so as I said, everything we've done so far has been using direct current, or DC, and that current flows in one direction. So many applications, such as the computer I'm recording this on, uses alternating current, where it changes over time. So, and conventional rotating generators, as we'll find out in topic 15, naturally produce a sinusoidal waveform. And so that's the most important thing to note here, that when you generate it, it actually is AC. Okay, from a traditional rotatory generator. Okay, so solar panels collect it in DC, and then you have to use a DC to AC converter, which you'll learn more about in 101 CDE, and you'll also learn about AC to DC converters as well. So how to convert an AC signal into a DC signal. So like basically, if you have an adapter or something. So here is a picture of an AC waveform. Everyone's probably seen one of these before from the A levels or the GCSEs even. So here we have the 0 point there, and it oscillates around this 0 degree point. So this distance from the 0 point to this peak here is called the peak value. So basically, how big is your amplitude of your waveform? So is it a small waveform like that, or is it a large waveform like that? You've got the peak to peak, which goes from one peak to another to give you the whole range of voltage, and the time it takes for one complete oscillation to be completed, so the time it takes to go up and go back to the same point, is called 1 period. Okay? So we can express that mathematically using this equation here. So Vt is equal to Vp sine omega t plus phi. Now, Vp is obviously that peak value that we were talking about just now. Sine is obviously the sinusoidal waveform. Omega is our angular frequency, which is equal to 2 pi f, as stated here, like so. And then you've got the time period, so you can find the instantaneous voltage at any point in time. And then you've got phi, which is a phase shift. Now, stereotypically, a voltage supply is set to 0 degree phase. And so it's more easy to calculate the phase shift induced by the components in an AC circuit. Okay, but that's the main part, and that's how you want to do it mathematically. I know I gave that away slightly by having it on the last slide, but what is the difference between the UK and the EU power supply? Here's a funny clip from Only Field Source. I'm not going to give the answer directly here. I'm going to go through that in the lecture. But here's a funny clip, so enjoy.
To your video recorder?
No, I haven't actually read them.
Well, why don't you do that small thing, Derek? I think you'll find it very interesting, because we had instructions in German, Spanish, French and Italian, and not one single word in English. And that's why your machine don't work. It was made strictly for sale in Europe.
But we are in Europe. We're in the common market, aren't we?
Yes, I know that, but we've got a different electrical system to the rest of Europe, and that's why your machine is on the blink. Its components are burning out. It is what's technically known as knackered. Willie Nelson's touched you up.
I don't believe it. Well, that's all I need, isn't it? You won't be able to sell the others now, Del. Too late, I sold them all this afternoon.
You've sold them?
70, 60 quid each.
You have to give the money back.
Why?
Because they don't work.
Well, what do you expect for 60 quid?
So yeah, funny clip. I don't think knackered is an actual electrical term, but it's quite funny to hear anyway. Oops, no, we don't want to watch it again. I thought I'll leave that in. Be quite funny to see. Okay, so the phase shift that we mentioned here, this phi term, can be measured in either degrees or radians. So when you're doing your calculations, make sure that your calculator is set to the correct mode for what you want it to be in, and there will be some instances that we'll talk about in this video that we're going to look at. So if you want to convert a degree in angles to a degree in radians, you basically divide it by pi, and you basically multiply by pi and divide by 180. So if you have a omega value of 2, you know omega is equal to 2 pi f, so our frequency is omega divided by 2 pi, so that would give us a frequency of 0.32 hertz. So this omega term is very important and one you need to remember. So an AC circuit is comprised of a resistor, inductor, and capacitor. It's in various different combinations. Okay, they'll be excited by a single source, so all the voltages and currents are also sinusoidal. So they'll have the same frequency. So the frequency of the amplitude, well, the amplitude might change because of the components, but the frequency will always stay the same. Amplitude can change, obviously, because if you've got voltage drops and things in the circuit, and from the impedance, which we're going to talk about later on, then you could get a change in amplitude, but the frequency would still be the same. So if anything could change the amplitude and also the phase shift. So if it's in line with the voltage source, if it's not, and that leads us to an expression which I'll come across later on. Oops. Yeah. So capacitors and inductors are the ones that make a phase shift. Resistances are in line with the supply. So you only give a phase shift if you have a capacitor or an inductor in your circuit. Waveform we've already mentioned that, so that's like the standard waveform that we've got. Cycle is each repetition. Period is the duration of one cycle, and it's denoted by the letter T, and it's measured in seconds. And the frequency is the number of cycles that occur in 1 second, and that is described as the frequency, and that's measured in hertz. Okay, and remember when you calculate about t, the period has to be in seconds as well. So for example, if you've got a 2 millisecond period, what's the frequency? So f is 1 over t, which is 1 over 0.002, which gives us a frequency of 50 hertz. So see, it's fairly easy. Most people have probably come across this, I think even as far as early as GCSE. So hopefully this is just recapping some of the information at this point. We've got angular velocity, which is related to frequency since omega is equal to 2 pi f. And so that's the sinusoidal quantity that recurs every interval of 2 pi or 360 degrees. So for the duration t, for one complete cycle of a periodic variable is assumed to be corresponding to a time angle of 2 pi electrical radians. So angular velocity is for tracing of a time angle. So I'll just measure now. The instantaneous value is essentially, if we go back to that equation, remember we had Vp sine omega t plus phi. If we put a time value t in, we can find the voltage at any instance in time. When we used to have an AC quiz as part of the coursework assessment, that used to be a common question that was asked. But now it's only a very small part, if any, of the examination. Peak value we've already mentioned, so that's Vp, so how big the peak is. Peak to peak value we've already mentioned. The next one is the root mean squared value. Okay, so when you're measuring an AC circuit, there's two different ways that you can measure it. Okay, so essentially, if you measured it with a multimeter, you'd be measuring what's called the root mean squared value. Whereas if you measured it with an oscilloscope, you would actually see and measure the peak value. So the question everyone's probably asking is, what is this root mean squared value that I'm on about? So it's explained here where it takes a number of samples, it squares each one of them, divides it by the number of samples to give you an average or mean, and then it square roots it. Okay, so that's equal to the root mean squared instantaneous value. Okay, so it's represented by this. So if you know what the RMS value is, you can convert it to the peak value or vice versa using this simple equation. So to find the RMS value, you take the peak value and divide it by the square root of 2. If you know the RMS value and you want to find the peak, you multiply the RMS by the square root of 2. Okay. Note this bit here at the bottom of this slide. So phasors can be represented using both the instantaneous or the root mean squared value. In practice, ammeters and voltmeters are calibrated to give RMS values, and it's more convenient to move the length of the phasor, the RMS, rather than the maximum. So phasor notations are usually expressed as RMS values, unless specifically stated otherwise. We'll go through some examples of that in the tutorial. Okay, so let's talk about the crest or peak factor, okay? And the peak or crest value of a wave is the ratio of the peak to the RMS value of the wave, and it's a trigonometric relationship. Sorry, be aware of the mathematics on this. Unfortunately, we can't get around that because with it being an oscillating waveform, it's going to have sines and cosines in. So remember that sine is equal to cos minus 90, and cos is equal to sine plus 90. So if you have a mixture of sines and cosines, what you have to do is change everything to a sine wave. That's what we work on. Everything works with a sine wave. Okay, so take that. So you've got this time you've got an I1, which is sine omega t plus 30 degree phase, an I2, which is a cos omega t plus 10 degree phase, and an I3, which is sine omega t minus 30 degree phase. So we convert that by adding 90 degrees to it, as we've shown here. So I2 will then become sine omega t plus 10 plus 90, which gives us sine omega t plus a phase difference of 100. So remember to convert everything to sine. That's the important thing to take from this slide. Okay, here's the first exercise which you can have a go at, and we'll go through the results in the lecture. And the second one for you to have a go at to keep you busy. Okay, so then this brings us to how to represent the interaction between waveforms of the same frequency. So as I said before, if you've got a sine AC source, it will excite the circuit and everything will have that same frequency. The amplitude and phase might be different, but the frequency will always be the same. Okay, so there's 3 different situations that you can come across. Okay, and I'm going to explain these to you now. I'm just going to talk generally. I'm not going to just read this out myself. You can read through that yourself if you want to, but I'm just going to basically explain it the way I would explain it in a lecture. So the 3 situations that you have are as such. So the first one is when you've got a system where the voltage and the current are in phase, and that's in a purely resistive circuit like the ones we've already come across, or if the capacitive component and reductive component cancel each other out. The second situation is where the voltage may pass through a value and increase to a time earlier than the current. So in that case, the current is said to lag the voltage, or the voltage is said to lead the current. And that situation is where you have a more inductive circuit. Okay, and the last case is where voltage may pass through at a time later than the current, so the current is said to lead the voltage. So note here it's in phase if it's with a resistive circuit. It's said to lag the voltage. Current lags the voltage if it's inductive, and current leads the voltage if it's a capacitive circuit. So there's the 3 different ways. It might seem difficult to figure out which case is which, but there's a nice easy expression to do that, and that is this.
What do we do, Cap?
We fight.
This is gonna end well. They're not stopping.
Neither are we.
So yeah, it's not quite civil war, but the expression is called civil. So the C stands for capacitor, and in a capacitive circuit, the current I is leading the voltage V. Okay, so in a capacitive circuit, the current leads the voltage. For an inductive circuit, so that's your L, then the voltage leads the current. Okay, so for an inductive circuit, which is L, the voltage leads the current. And it's a really useful expression because it will help you when you're doing calculations. So if you have a more capacitive or inductive circuit and you get an answer for the voltage supply and for the current, it will help you determine if your calculation is right or not by just looking at that expression and seeing how that works. So how do you actually calculate this phase shift? Okay, first thing is you'll need a ruler. Okay, no other thing you need to bring to the exam for this bit is a protractor. These two things are incredibly important, and I don't know why I didn't turn my Outlook off, but never mind. So these two things are very important, okay? You need this for helping to draw phase diagrams, so you need to find the length, and this will help you with the phase angle as well. So these two things are very important. But we're going to put the protractor down for the moment, and we're just going to focus on this. So, as you can see here, you've got VT, which is 0.4 sine omega t of a phase shift of 0 over 180. And there we've got I is 0.8 sine omega t plus 45 degree phase shift this time. So if we didn't know, if I hadn't typed this into MATLAB, how would we know that that is actually a 45 degree phase shift or some form of phase shift? So we look and we know what this period is, which is represented by this purple arrow here, double-headed arrow here. So that's the period, so the time it takes for it to go around and oscillate once. And this is the phase shift between the two. So if you get your ruler, you can go on your screen, you can measure the distance that it takes for the period, measure the distance it takes for the shift, and you can find what proportion of the difference is of that whole period. Because you know one period is 360 degrees. So here is, let's put that back. So here's some calculations. So this is basically what I've said. So when I did this on the computer screen, I measured the distance for a period as 5.7 centimeters. The distance for the phase shift is 0.75 centimeters. So when I plugged that in, I got an angle of 47.3 degrees, which is pretty good, considering it was 45, and the fact we're measuring it with a ruler. On the lecture note, again, I printed the lecture notes off. I tried it again, got a distance for the period of 3.8 centimeters, a value for the phase shift as 0.5 centimeters, and again, it gave me a 47.3. So it's still a very good method, and that's why this is highlighted in one of the theory assessment tabs. Another way you can mention it here, I'm just taking the equation, so I've got my VT A sine omega t term, and I've got omega t plus the phase, so I've highlighted the bits I need. So my amplitude is my 0.4 and my phase is equal to 0. Okay, so they're the two important things, so the peak and the phase. Okay, so when you draw a phasor diagram, and when you write phasors, you'll put the magnitude, and then you'll have a special character where you put the phase in, and we'll do more about that in the tutorials themselves. Already covered that. So if you wanted to use that method, you could find it from an oscilloscope. You can also you could take phase shift from an oscilloscope by using the inverse of the sine function, so A sine. But note that you would have to normalize for waveform to unity first. So yeah. So basically, this is what I've been saying. Phase diagrams, as I said, show the phase relationship between the current and voltage, and they can be represented by a diagram. The usual reference for a zero phase is taken to be the positive x-axis. So why do we need it? Because integration and differentiation might be horrible, but they become really simple algebraic operations, which is not the case with sine and cosine. So basically, our Ohm's law reduces to this here. So we've got V equals Zi. Now Z is the term for impedance, and impedance is the AC version of effective resistance. So a resistor, a capacitor, and inductor will all have impedance values related to them, and I'm going to go through the equations for that in topic number 10. Okay, but there's also a term called X, which is reactance. So there's a difference between reactance and impedance, and I'm going to go through that when we come to that later on in the module. Remember, phasors are only useful for finding force responses only. They're not good for natural responses, so you basically can't use them if you don't have some form of source to excite the circuit. A phasor analysis may be used to find the steady state response only with stable circuits. So basically it has to be in a stable circuit, not a circuit that's growing out of control or a circuit that's damped and is slowly oscillating down to a damping point. So it can only be used for a force response only, and only for steady state or stable systems. As I said before, so we take the magnitude, the phase, and we write it like that. So here we have the A1 to the phase angle of phi1. Okay, so the length of the vector represents the RMS amplitude, and the angle of the vector represents the phase angle. So that's how we will draw it. Again, assuming that A1 is an RMS value. Okay, so that's important because if you want to draw them on here, that's why you need to know the length of a system and the angle which it points at. Okay, so here's some examples. So red is a phasor vector of 1.26 to the phase angle of 71.57. So there's 90 degrees, 0 degrees, 90 degrees, 180 degrees, 270 degrees, and back around again. This could also be minus 90 degrees as well. So it goes in an anti-clockwise direction, and this line here represents the value of 1. This one here represents the value of 2. Then the outer ring represents the value of 3. We'll be using something similar to these in the tutorials, but they're a lot smaller in value. Okay. The other thing as well when you look at this is this line here from a 0 to 180 degree point. When we're plotting things in complex number terminology, which we'll do in topic 10, that is your x-axis, which represents your real numerical number values, whereas the 90 to 270 line represents your imaginary axes. So that's where your imaginary numbers are, and we'll come across the complex numbers in topic 10, but I want to introduce that concept to you here and now. So if we look at number 2, which is the blue dude, it's 5.27, 2.52. There's my autism kicking in slightly there. Sorry about that. So 2.52 to the phase angle of minus 18.43. So its length is 2.52, and it's got a minus 18 degree angle. So you start at 0 and you go back down there to the minus 18 point there. Okay, and the green and the black dude here, this black vector is 0.632 to a phase angle of minus 18.43 again. So it's exactly the same as the blue dude, except it's smaller in magnitude. Okay, which is why these two are overlaying each other. Okay. So a general phasor expression for impedance. Okay, so let's have a look at this. So it does use a bit of trigonometry, but don't worry about that. So here's a general phasor expression for impedance, as we said. So essentially, you've got V, R, which is the voltage across the resistance, which is equal to IR, which is in phase with the current. You've got VR, which is a voltage across the inductor, which is a IX, which is leading by 90 degrees. So X is this reactance term, as I've said. X is a term for reactance. And impedance is when we actually have the direction included in it. Good old Ohm's law still works here. So we've got I is V over Z. So instead of replacing V over R, we've got V over Z. The law still works perfectly for AC circuits. So we can calculate Z because we know what R is, we know what X is, by using phi is equal to arctan of X over R. And our Z term here, we get from trigonometry, is Z equals the square root of R squared plus X squared. But that only works if you have a square angle rectangle between the two. And the bottom point on this is that the phase angle of the voltage supply is usually set to be 0, as I've already said, to make it easier to calculate your shifts. Here's another important slide. So this is, you'll see this quite a lot in the tutorials. As I've said before, the 180 to 0 line is your x-axis, which is your real coordinate, and your y-axis from 90 to 270 is your imaginary axis there. And these two are two very, very, very important equations to look at. So here we've got a green dude and a purple dude. So let's look at the green dude first. So our magnitude is how long our green dude is. So here's our green dude, and as you can see, he's got a magnitude of 1 in length. And he's at a phase angle of 240 degrees. However, if we wanted to find the complex numbers for that, so if we look at our real axis first, we can follow that along to here, which, as you can see, is 0.2, 0.4, so minus 0.5, because this point here is your 0 point. So anything up here is a positive imaginary number, anything here is a negative imaginary number, anything here is a positive real number, and anything over here is a negative real number. So this is a number of minus 0.5 on the real axis, and if we go across again here, we've got minus 0.9 on our imaginary axis. So our complex number for this would be minus 0.5 minus 0.9i. That's an interesting point as well with complex numbers. If you wanted to use a mathematical package like Wolfram or MATLAB, you have to make sure that you use the I terminology, because that's how mathematicians represent it. Unfortunately for us, I represents current. So engineers usually use the term J to represent a complex number. Okay, so be aware of that. If we look at our purple dude and apply the same philosophy, so if we want to find our real coordinate, we could. So he's 0.8 in length to a phase angle of 30 degrees. So if we go down from this point here, this gives us 0.2, 0.4, 0.6, 0.7 on our real axis. If we go across here to find our imaginary number, it's 0.4. So the coordinates of our purple vector or purple dude would be 0.7 plus I of 0.4. Okay, so then if you have those coordinates and you want to draw them, then to find the magnitude, you would do the square. If you want to add them together, you could add them together to find the new coordinates, or you could do it this way. I personally would add them together to find the new coordinate. Then it's the square root of the real part squared plus the imaginary part squared to give you the magnitude, and then our phase would be tan to the minus 1, or arctan, of the imaginary part divided by the real part, which is what happens here. So this is how you would add two vectors together, and we'll be going through this more in the tutorial. So that's it for me for video number 9. So I hope you found this interesting. See you soon for another video. Take care, guys. Have a good night. Bye bye.